We are going to first talk about isolation transformers, and then we will solve one or two numericals. So we have studied transformers. We know what exactly the transformer does is it transforms voltage from one level to another level at constant frequency. The frequency that remains constant. So particularly when we talk about an isolation transformer, so this will be also a transformer which will be using for transferring electrical power from a source to some electrical device, or you can say some equipment. The important thing is that it is going to isolate the powered device from the power source, the device which is going to receive the power, and the power source that will be isolated. The reason is it is for safety purpose. So basically the isolation transformer, it is going to provide the galvanic isolation, that is there will be no conductive path present between source and load in the electrical system. Mostly isolation transformer that operates with turns ratio equal to 1. It can work like a transformer. The principle that would be would be similar to transformer. So it is going to operate in the same way a transformer operates. The particular application about this transformer that will be used to protect against electrical shock. Already we said the isolation transformer is used or considered for safety purpose. So it is going to protect against electric shock. It suppresses electrical noise in sensitive devices. It can use to transfer power between two circuits which must not be connected, basically isolated. A transformer sold for isolation is often built with special insulation between primary and secondary windings, and it is specified to withstand a high voltage between primary and secondary windings. So in construction point of view, there will be some special insulation that will be introduced between primary and secondary winding. So what would happen, this isolation transformer that would block transmission of the DC components in signal from one circuit to other circuit, and this is going to allow the AC component in signals to pass. So basically it is isolating two circuit power from the load, and it is going to block DC component, allow AC component to pass from one circuit, means primary to secondary. Basically you can think in that way. Its application, basically it can be used as a pulse transformer. You might have heard 1:1 transformer, the pulse transformer. It is also having the voltage ratio or turns ratio equal to 1 that we have seen. So it can be used, pulse transformer, in power electronic circuitry. You are using the pulses or train of pulses. It is used, application could be in electronic testing. It can used in supply of equipment at elevated potential, medical purpose you can use. It can be used in CRO. You might have observed that it is isolated, the ground is different basically. So isolation transformer is used there. Here you could see one application in SMPS where two circuits are shown. We are not going to discuss what exactly this circuit is consists of, but there will be the two part. One on this side you could see, that is the primary non-grounded reference, and the second one is the secondary ground reference. So here is your transformer. You could see that this is basically your isolation transformer. There will be three voltages. There are three different windings on this side, and on this side it is a one winding. So it is basically isolated. So here the isolation transformer comes into the picture. So that is all about isolation transformer. Now we are going to discuss a numerical. So that will be on auto transformer. We already seen that a two winding transformer can be used as a auto transformer. So to understand and clear our concept, this particular numerical we are going to consider. So the numerical is a 20 kVA 2300 oblique 230 volt two winding transformer is to be used as an auto transformer with constant source voltage of 2300 volt at full load of unity power factor. It should be the power factor. Calculate the power output, power transformed and power conducted. If the efficiency of the two winding transformer at 0.6 power factor is 96%, find the auto transformer efficiency at the same power conducted, not it should be conducted, not collected. So basically what is given, a 20 kVA transformer is given which is having voltage ratio 2300 by 230 volt. A two winding transformer is originally given to you, and this transformer is going to use as an auto transformer. Two winding transformer is with you. Now you are going to use this transformer as auto transformer, which will be having constant source voltage of 2300 volt. So now it is very quite clear that two winding transformer will be converted to auto transformer. So at that time you have to determine what will be the power output, what will be the power transformed. We have seen, we know very well that in case of auto transformer, a part of power is going to transform from one circuit to another circuit through transformer action, and the rest of power that will be transformed through conduction. Okay, that is very clear to us. That's why what will be the power transformed and power conducted. Transformed means through transformer action, conducted means conduction. Another part we are going to discuss later on. So I think the things are clear to you. It is quite clear. So what you can do, you are having two winding transformer and you are interested to use it as auto transformer. So what would happen? What you need to do in order to obtain auto transformer, the two winding that will be connected in series. So once it is connected in series, you will get single winding, as auto transformer consists of only one winding. So one winding should be there. So both winding, primary as well as the secondary winding, that will be connected in series. So your transformer will become auto transformer. So first let us write down all the data, what are the given data and what we have to determine. So what is given? The rating of transformer is given, that is 20 kVA. Voltage ratio is given 2300/230 volt. While transforming the two winding transformer to single winding transformer or auto transformer, the applied voltage is given 2300 volt. Remember, the applied voltage is given 2300 volt when two winding transformer is going to be used as auto transformer. So what here we have to determine? We have to determine here the power output, means kVA rating, that has to be determined. The power transformed, the power which is going to transform using transformer action, that we have to determine, and the power conducted, that has to be determined. So this is part A, we can call it. In another part, if the efficiency of the two winding transformer at 0.6 power factor is 96%, find the auto transformer efficiency at the same power. So basically we have to determine what will be the efficiency of converted transformer, that is auto transformer, when the two winding transformer was having efficiency of 96% at 0.6 power factor load. So one by one we are going to see it. Hope the question is quite clear to you. How we can solve that we are going to think. So first what we have to do, the two winding transformer, that has to be converted into single winding transformer. So connect both the winding in series, you will get this circuit diagram. Okay, so you are having this circuit diagram here. While preparing this circuit diagram, you have to keep it in mind that the applied voltage is of 2300 volt. So 2300 volt, that will be your applied voltage. And the transformer, two winding transformer has two winding, one is 2300 volt and another one is of 230 volt. So 2300 volt, it means this is your high voltage side basically. So the high voltage side, that will be connected to the supply. So here you could see that what we have done, that in this circuit diagram you could see that 2300 volt is connected to this winding. HV side you can say 2300 volt is connected. So which one is remaining? The 230 volt winding is remaining. So 2300 volt winding will be connected in series with 230 volt winding. So this will be your winding. You can call this BC as your primary winding. The primary winding is that winding which is connected with the source. In this case, the high voltage winding is connected with the source, so that the primary winding will be your BC. Is it okay? I think there is no doubt. We know already these things. So the remaining, this winding, the low voltage winding, that will be your secondary winding. Means output that will be taken from here. It will be connected between this A and C. So the load will be connected in this way. I think drawing this particular diagram, it is not that difficult because the things are given. So just give little bit thinking, think over it, you would be in position to do this. So what we will do, in order to determine the kVA, the first thing is that we have to determine the output. So for determining the output, what is needed? The voltage and the current is needed. So what will be the voltage? The voltage, this output kVA you are interested, output power you have to determine. So output voltage and output current. So whatever voltage will appear across this load and the current which will be flowing through this, that will be your output kVA. That will give you output kVA. Okay. So in order to find that, what we need to first determine, we need to determine how much voltage will appear across the load. We are having two winding transformer. Okay, so already we know that the 2300 volt, that will be in primary and the 230 volt, that will be in secondary. So for this particular diagram, what we have drawn, the polarities are marked. What will be the voltage? That will be the addition of these two. You can apply the KVL basically here. So this voltage 2300 plus this voltage 230, that will give you total voltage across the output. Okay, then voltage is with us. We can now we have to determine current. So current, that will be the current flowing through the load. So what would be the current which is going to flow through the load, which is flowing through this winding, the secondary winding. So we need to determine the current in secondary winding. And what would be the current in secondary winding? Which is coming from the supply that will be basically distributed to the secondary winding and primary winding. So what we need to determine, first we have to determine the rated current in both the windings, primary winding and secondary winding. So once we are having the current in secondary winding, we will be in position to calculate the output kVA. Okay, so we have obtained this voltage is already we have obtained for this given polarity. Polarity is marked by us. Okay, so for this, how much you got? You are going to get 2530 volt. I think this is quite clear to you. So what we got 2530 volt. That is going to be appear across the load. Then we are going to calculate the rated current in HV winding. So how it can be calculated? The power rating is given for the 2 winding transformer. It was 20 kVA. So 20 kVA divided by the voltage, it will give you the current into that winding. So what was the voltage? 2300 was the voltage. 20 kVA was your power. So it will give you 8.69 ampere. So the 8.69 ampere, that is current in your primary winding. Then okay, it should be LV. Okay, here it should be LV, not HV. So the rated current in LV winding, in the same way you can calculate, it will come around 86.9 ampere. What you have to divide by which voltage? That is the voltage across the secondary winding. So that is 230 volt. So it will give you 86.9 ampere. So it is quite clear that 86.9 ampere, that is going to flow in this LV winding, and here in HV winding 8.69 ampere is going to flow. So that is very clear to us. Then the primary and secondary winding, that is clear to us. Now what we will do, we are going to apply KCL at this point. We are going to apply KCL in this point. So we will be in position to calculate how much current it is drawing from the supply. So apply the KCL here. Okay, so what would you could see for the given direction, here the current is going outwards. This is the incoming current I1, that is incoming current. This is the outgoing current. So ultimately the current which is drawn from the supply, that will be the summation of these two currents. So what we are getting by adding these two currents, the resultant will be 95.59 ampere. Okay, so this is your input current. Now we are in position to calculate the kVA rating, auto transformer kVA rating. So what it will be? Voltage multiplied by current divided by 1000, that is for just getting the kVA. So what is the voltage here? Voltage is here across the load, that is 2530. Okay, and the current which is flowing through this load, that will be your this current, secondary current. So what is the secondary current? That is 86.9 ampere. Just multiply it, you are going to get the rating of transformer 220 kVA. Is it clear? Hope the things are clear to you. There is another way by which you can calculate this rating. Okay, so the input is here. You could see the kVA rating of transformer, output input, it is the same. So what would be the input? The applied voltage is 2300 multiplied by the current in primary, primary winding. Yes, it is primary winding. So multiply it, you are going to get the same value. It will be the same, whatever way you want to calculate. So we have calculated auto transformer kVA rating. So what will be the output power? Output power, that will be kVA multiplied by power factor. So the power factor is given unity. So kVA multiplied by 1, that is 220 multiplied by the 1, it is going to give you the output power. So what it will be? 220 kilowatt. Then we have to calculate the kVA transform. So in order to find the kVA transform, which one is the primary winding? The primary winding is here BC. Okay, so by transformer action, how much kVA is going to transform to the secondary winding, that is your AB winding, that we have to determine. So how we can determine that? We the voltage corresponding to this winding, 230 volt for the secondary winding, multiplied by the current, it is 6.9 divided by 1000, that is going to give you the kVA transform. So how much kVA is going to transform? It will be your 20 kVA. It will be 20 kVA. How we have calculated? We have calculated that the voltage, corresponding voltage for this winding, corresponding current for this winding, so that will give you kVA. The alternative way is what? You can calculate, multiply this 2300 volt multiplied by the corresponding current here divided by 1000. So this is going to give you 20 kVA. You can solve it. Okay. Power transform, just multiply with power factor to this kVA, so that will be power transform. So it will be 20 kilowatt. Then what will be the kVA conducted? You know total kVA. What is the total kVA? That is a 220 kVA. Out of this 220 kVA, the 20 kVA is transformed through transformer action. So rest will be the kVA conducted. That's why just subtract 20 from this 220 kVA. So you are going to get 200 kVA. That will be basically kVA conducted. Is it clear? I think there is no doubt. And what will be the power conducted? That will be multiplied with power factor. So it will become 200 kilowatt. So what you have noticed here, your transformer, that is of 220 kVA. Okay. So out of 220 kVA, only 20 kVA is transformed using transformer action, and the remaining, that is 200 kVA through conduction. This is the difference when you are talking about two winding transformer and auto transformer. The other thing, the important thing, if you have noticed, what was the rating of two winding transformer? In given numerical, what was the rating of the transformer? It was 20 kVA, correct? And what is the rating of auto transformer? It is 220 kVA. See, significant transformation in the rating of transformer. So it is the 20 kVA transformer becomes 220 kVA transformer when the 20 kVA two winding transformer is converted to auto transformer. Is it clear? What is the observation here? Why this numerical is taken here? To understand auto transformer clearly and the difference between two winding transformer and auto transformer. So here transformation of certain power, that will be through transformer action, and some majority, you can see from this numerical we could conclude in this way that majority of the power that is transferred to the secondary circuit through conduction. Only a small portion is through this one. Now what we did here, we have taken the polarity like this one. Okay, we said we have assumed some polarity. It is possible you can consider a different polarity what we have shown here. This one. Earlier, this case we have considered. It is possible that some of you may mark the polarity in this way. Okay. But remember one thing, the load current, the direction of load current is not going to be reversed. It cannot be reversed. The direction of only the supply current, or you can say the current in the primary winding, that is going to be reversed. But the load current, it cannot be reversed. Okay. So the polarity is different here. You could see what we have marked here. It was plus minus for the secondary circuit. Here we have shown plus minus, and here it was the plus minus. So of course the direction of current is basically changing. So the question is here whether it is going to change the output of power or it will remain same. That is the question here. The marking of the polarity means the connection of the winding, basically you could consider in that way. That is different. Earlier you have connected two windings in series in this fashion. Now it is connected in this fashion. Okay. So the question is that whether output of the resultant transformer, that is auto transformer, is it going to change? Let us find out through this numerical. Okay. So we are going to follow the same process what we have done in earlier case. So what we will do for this HV polarity, again we are going to find out the voltage across the load. So what would happen when you will apply the KVL here? Instead of addition of EMF, there will be subtraction. So ultimately what value you are going to get it? It will be 2070 voltage. The reason is obvious because EMF are opposing each other. Okay, you can see the plus minus. Just apply, if you are moving from this direction, so negative to positive it will be positive, and from positive to negative it will give you minus sign. So definitely you are going to get 2070 voltage. What would happen to the rated current? It is not going to change because the two winding transformer, whatever is the voltage ratio, that voltage ratio is going to be same. The rating of power is not going to change. So the current, that will remain same. That's why we have not calculated again the current. So the current, that will be the same here. The only thing what is happening, the secondary winding, that is reversed, so that its MMF is going to reverse. Already we said that the load current I2, that cannot reverse, so that the primary winding current is going to reverse. Okay, these things are there. Now what we will do, what we have done in earlier case, we determined the current, the value of the current which is drawn from the primary, that we are going to determine. So what you have to do, you have to apply the KVL at this point. Now you could see that what is the current, this one is incoming current, this one is your incoming current, and this one is your outgoing current. Okay, so ultimately what you will get, there will be the difference of these two currents, that is going to give you the resultant current. Means the current which is drawn from the supply, that is less in this case. This is 78 ampere approximately, and in that case it was the sum of this one, so 94 or 96 ampere something you was getting. So the current which is drawn from the supply, that is reduced. Then we can calculate the rating of transformer in the same way. The voltage multiplied by the current through the load, that will give you the rating. So how much you are getting? It is 180 kV. Alternatively you can calculate using this method. So okay, in this 2070 divided by 86.9, that is this case, and you can calculate in this way, 2300 multiplied by this current, the input current, that will give you the rating. Remember, you have to use the input current here, input current, input voltage, so only you can get the input kVA, output kVA, output voltage, output current, that will give you the output kVA. So what happened here? The rating of transformer, that is reduced. The same transformer which was connected earlier in the fashion what was shown there, at that time you was getting some higher rating, 220 kVA, here you are getting 180 kVA. Okay, so what is the conclusion here? Connection, how you are connecting the winding in series for two winding transformer, that is going to affect the output of transformer. So other things can be calculated in similar fashion. The power output at unity power factor is multiplied with the power factor into the kVA, so that will be 180 kilowatt. how much kVA that will be transformed. So in the similar manner you can calculate your voltage multiplied by the current. So transformed kVA, that is coming 20 kVA. What was the case? How much you was getting in previous case? It was also 20 kVA. So what you can conclude from this, that it remains same. Whatever is the conduction or connection, the transformation of power, that is same in both the case. It is 20 kVA and 20 kV. So output power, that will be 20 kV multiplied by your power factor, 20 kilowatt, that will be your output power or power transform. Basically it is not output power, power transform. And the kVA conducted, total kVA we have calculated 180 minus 20, that will be 160. So it is the kVA which is conducted that is reducing here. I think it is clear to you. And power conducted, that can be given. So the same observation you can made here. Out of 180, only 20 that is transformed through transformer action. 160 kVA out of 180, that is through conduction, and the rating is 180 kVA. So 20 kVA transformer can be converted into either 180 kVA transformer or 220 kVA transformer. So this is the outcome from our conclusion from this numerical. I think that things are clear to you. Okay, so you can solve the numericals in this way. Those who are in online mode, if you are having any question, you can ask. Now let us consider one more example. Okay, one part is completed. What we have done, there were two parts. One was where we have to calculate the power output, power transformed, and power conducted. The second thing, we have to calculate the efficiency for these transformers. For both the connection, we are going to determine the efficiency and see when two winding transformer was used at that time what was the efficiency, and when we are going to use it as auto transformer, what is the efficiency. Okay, so let us see how we can determine it. So what is the efficiency formula? Efficiency is output upon input. Input can be written as output plus losses. See what is given. They have given the efficiency is given. So how we can proceed? We can proceed with the losses that will be calculated from this formula only. So first we are going to calculate the losses because it is not given. So losses can be calculated if the efficiency is known to us, and yes, efficiency is given. So that can be calculated, as well as output is also calculated because the load power factor is given. The power factor is given over here. So what will be the losses in two winding transformer? That will be, just substitute the value here. The efficiency is 96%. So here the 96, that will be 0.96. That will be there, and the output can be calculated from your 20 kVA and this power factor. So 20 kVA multiplied by 0.6, you are going to get the losses in transformer. So 500 watts are the losses. Now we are operating auto transformer at same voltage and same current, or you can say rated voltage and rated current. So think whether the losses in auto transformer is going to change. If you are operating auto transformer at rated voltage and rated current, so the losses, is it going to change? No, it is not going to change. So the losses that will remain same in case of auto transformer. So you can consider the same losses which was occurring in two winding transformer. So now losses is with us, so I think we are in position to calculate efficiency of transformer. Okay, output is known to us. So when there is 220 kVA rating, in one case we got 220 kVA auto transformer. So for that, what would be the efficiency? You can use the formula 1 minus losses upon input. Just substitute the losses value, it is 500 watts, and the input, what it will be, the input will be your output plus losses. So output that will is of 220 kVA multiplied by the power factors. Remember the power factor will remain the same here, 0.6. At same power factor you have to calculate the efficiency. So 0.6 plus losses 500. So how much you are getting? You are getting the 99.623% efficiency. So what you can see, when you are using the same transformer as auto transformer, the efficiency is increased from 96% to 99.6%. Also the rating is increased 20 to 220 kVA. For 180 kVA, sorry, it should be 180 not 280, it should be 180 kVA. Okay, so for 180 kVA transformer, what is the efficiency? In the same way you can calculate, and it is coming 99.54%. It is slightly less than the efficiency for 220 kVA transformer. It is slightly less than, but it is higher than the efficiency of two winding transformer at same load power factor, So these are the conclusions that you can keep it in your mind. I think the things are clear to you. So we are going to stop here. Only if you are having any questions, you can ask. Otherwise, we can stop here.